Welcome to section 7.4, Properties of Logarithms. At the end of this section, you should be able to answer these questions. What is the definition of a logarithm? What are the properties of logarithms? How can we use the properties of logarithms to solve equations, both logarithmic and exponential? Why do we need to check for extraneous solutions when we solve logarithmic equations? Let's start with the definition of the logarithm. Well, the definition of the logarithm is that the logarithm base b of x will equal y if and only if b to the y equals x. And we have some restrictions. B has to be greater than 0, not equal to 1, and x also has to be greater than 0. So what we're saying is that the answer to a logarithmic expression, so this answer is actually an exponent. So when we evaluate a logarithm, we are determining an exponent. Let's review the properties of logarithms. Log base b of x raised to the y can also be expressed as y log base b of x, which means that we can take our y value, our exponent, and bring it down in front. Log base b of x times y can be rewritten as log base b of x plus log base b of y. And log base b of x over y can be expressed as log base b of x minus log base b of y. Log base a of x can be rewritten in terms of other logs using our change of base formula. The change of base formula is log x over log a, or natural log of x over natural log of a, and can actually be written using whatever base we want to create these ratios. Typically we see log or natural log because those are the two logarithm bases that we have available on our graphing calculator. Now let's work through a few examples so that we're comfortable working with logarithms. Here's the first. Write log base 5 of c equals a in exponential form. Now for me, I establish a relationship in my mind where the general relationship between these three values, 5, c, and a, looks something like this. Log of the base gives me a result if I've raised to a power. So the way I remember this is the base, the result, and the power. B, R, P in that order, or burp. So when I'm given a question like this, I think to myself, all right, it's time to burp. So in this case, the base is going to be 5, and the power that I'm raising 5 to is going to be a. And then finally, my result will be c. So my new relationship is 5 to the a equals c. All right, so let's take that in the opposite direction. Here we have z to the 4th equals m, and we want to write it in terms of the logarithmic relationship. Well, if I burp it, then my log base is going to be z, and my result is m, and that came from a power of 4. Log base z of m equals 4. Now let's start working with the properties of logarithms. Here we have log base 3, or log of 3 plus log of 5 should be equal to log of 3 times 5, our multiplication property of logarithms. Well, since they're asking us to show numerically, that means we need to determine the numerical values and check to see if they're the same. So let's pull out our calculators, and we will find the log of 3 and we will add the log of 5. Now that log without a base attached to it, we remember is log base 10. So my calculator tells me that this is 1.176091259. Now, let's compare that to the log of 3 times 5. So log 3 times 5, which we know is 15, turns out to be the exact same value, 1.176091259. So we have shown that those two values are the same. The multiplication property holds true for this example. Now let's prove algebraically that log base b of x times y is log base b of x plus log base b of y. To prove this relationship, let's start by saying that we're going to take log base b of x and we'll call that c. And we'll take log base b of y and we'll call that d. Now, if we burp both of these equations and write them as exponential relationships, then b to the c equals x, and b to the d equals y. Now, if I multiply x and y together, I would get b to the c times b to the d. And we know that when we multiply two numbers with the same base and different exponents, we can add the exponents. So we could write x times y as b to the c plus d. This relationship, xy equals b to the c plus d, we could also write as a logarithm. If we go back and write this as a logarithm, then log base b of my result, xy, is c plus d. But c plus d is also log base b of x for c and log base b of y for d, which was the expression we were trying to establish. Let's move on to another example. How do we simplify this expression log base 3 plus log 7 minus log 5 to a single logarithm expression? Well, we apply the properties of logs. First of all, log plus 3 plus log of 7 is a sum which can be rewritten as a product. So log of 3 times 7 minus the log of 5. Now we have a difference which can be written as a division expression. So log of 3 times 7 over 5, which is log of 21 over 5, or sometimes written as 4.2. Let's take a look at another possibility. Here we have an equation, 4 minus 3 times the natural log of x plus 5 equals 1. So to solve this, we want to also work our way into an exponential expression. So we're going to burp the relationship once we have it in a form where we can do that by applying properties of logs. So we start by isolating our natural log expression. So I'm going to subtract 4 minus 4, and I get negative 3 natural log of x plus 5 gives me negative 3. Then I'm going to divide both sides by negative 3, and I get the natural log of x plus 5 is equal to 1. Now I rewrite the expression in terms with an exponential relationship. So that tells me the natural log has a base of e. I'm raising it to the power of 1, and that equals x plus 5, which means that x would be e minus 5. Which if we evaluate in our calculator becomes negative 2.2817. Our next example is another equation that we would solve, and here again we'll apply properties of logs. Here, since I'm adding two logs with the same base, I can express that as a multiplication problem. So log base 2 of x minus 1 plus log base 2 of x minus 3 can be written as log base 2 of x minus 1 times x minus 3, and that would equal 3. Here I go from this expression to an exponential relationship. So my x minus 1 times x minus 3, my result, is equal to 2 to the third power. If I expand, I get x squared minus 4x plus 3 is equal to 8. To solve my quadratic, I subtract 8 and set it equal to 0. So x squared minus 4x minus 5 is equal to 0. I factor and I get x minus 5 times x plus 1 is equal to 0. So my possible solutions here are x equals 5 or x equals negative 1. Now, in the process of solving this equation, I moved from a logarithmic expression here to an exponential expression. The problem there is that for an exponential expression, all values of x are possible. But in a logarithm, we can't take the logarithm of a negative number or 0. Those are not within the domain. So these two possible values for x, 5 and negative 1, need to be tested in my original expression, the log base 2 of x minus 1 plus log base 2 of x minus 3, to see if they violate our domain restriction. If I plug in 5 to my original expressions, I get the log of 4 plus the log of 2, and that's fine. But if I plug in negative 1, I get log of negative 2 and the log of negative 4, neither of which can be evaluated. So this second solution of x equals negative 1 is not an actual solution. We call that an extraneous solution. So my final answer to this question would be that x is 5. X equals negative 1 is not an actual solution. Let's look at another situation. Here in our question we have the difference of logs. So we can write the difference of logs as a division expression. So log of x minus 1 over x plus 2 is equal to minus 1. And if I write that as an exponential expression, I burp it, then my base here is 10. So 10 to the minus 1 is equal to x minus 1 over x plus 2. I can rewrite that 10 to the minus 1 as 1 over 10. And I can get to to solve this, I can cross multiply. So 10 times x minus 1 is equal to x plus 2. 10x minus 10 equal to x plus 2. Subtract x's, 9x, add 10 is equal to 12. So x is equal to 12 over 9, which turns out to be 4 over 3. Now, we did go through the process of removing our domain restriction. So we should go back and check our 4/3 to make sure that our original expression can be evaluated. 4/3 minus 1 is a positive number, and 4/3 plus 2 is also a positive number. So the single answer we arrived at is a valid answer, not an extraneous solution. How do we evaluate an expression if we don't have the capability with our calculator to directly input the logarithmic relationship? Let's suppose, for this example, that the natural log key on our calculator somehow became non-functional. How would I find my answer? Well, by using the change of base. Here, natural log of 29 can be rewritten as log base 10 of 29 over log base 10 of my original base, or e. When I put that in my calculator, I would say log of 29 divided by log of e, which is right above the division sign. And I get 3.3672953. Miraculously, my natural log button is now functional, so I could test then by asking for the natural log of 29. And we get the same value. Here we have an exponential equation where our variable is in the exponent and we want to solve for x. Here's where the properties of logs allow us to do that. If I rewrite my expression of 7 to the 3x equals 983, that's saying log base 7 of 3x of 983 should be 3x. Now I don't have a log base 7 key on my calculator, so I could use the change of base formula here. And that would tell me that log 7, or log 983 over log 7, should equal 3x, which means that x then would equal log 983 divided by the log of 7, and also divided by 3. That turns out to be 1.1803, and you can check that in your calculator. Another equation where we need to solve for x. Here we're going to approach this one a little differently. Here I've got 3 to the x minus 2 equals 9 to the x plus 1. And it's hard to evaluate or approach this unless I'm looking at a problem with similar bases. So I can think of this problem, rewrite it as 3 to the x minus 2 is equal to 3 squared to the x plus 1. So here, now I've got the same bases, and if I simplify the expression on the right, when I raise an exponent to an exponent, I multiply. So 3 to the x minus 2 is equal to 3 to the 2x plus 2 when I multiply my exponents. If I have the same bases and it's supposed to be equal to each other, then my two exponents should also be equal to each other. So x minus 2 should equal 2x plus 2. Solving for x, subtracting x on both sides gives me x, and subtracting 2 gives me negative 4. So x should equal negative 4. Let's look at a final example. Here we're going to try to solve the equation e to the 2x minus 3e to the x plus 2 equals 0. And the way we're going to solve this equation is to recognize that what we're actually looking at is a quadratic equation. Here, e to the 2x can be written as e to the x squared minus 3 e to the x plus 2 equals 0. Now, let's look at that e to the x. Let's simplify this equation by replacing e to the x with some variable. I'm going to use q. So if e to the x equals q, my equation by substitution would be q squared minus 3 times q plus 2 is equal to 0. That expression can be factored to q minus 2 times q minus 1 equals 0, leaving me with possible solutions of q equals 2 or q equals 1. Which is great, but my equation was in terms of x, so I need to know which values of x are going to satisfy these expressions for q. Well, if q equals 2, then e to the x equals 2, and if q equals 1, e to the x equals 1. Now here, to solve for x, I can take the natural log of both sides, and I would have the natural log of e to the x equals the natural log of 2, or the natural log of e to the x equals the natural log of 1. I can bring the x down in front by the properties of logs, so x natural log e equals the natural log of 2, and x natural log e equals the natural log of 1. Here, that's the natural log of e means what power do I raise the base e to end up with e? Well, that's just 1. So the natural log of e is 1. X equals the natural log of 2. And over here, x would equal the natural log of 1. And to end up with a result of 1, then the power has to be 0. So my solutions are x equals the natural log of 2 or 0. All right, time for a recap. What is the definition of a logarithm? Well, as we established, a logarithm is an exponent. So when log base b of x equals y, y is an exponent. What are the properties of logarithms? Well, our properties of logarithms are these. When I have log base b of x to the y, I can bring the y out in front and write the expression as y log base b of x. Log base b of a product, x times y, can be expressed as a sum, log base b of x plus log base b of y. Log base b of a division problem, log of x over y, can be expressed as log base b of x minus log base b of y. And then we have our change of base formula. Log base a of x can be rewritten as log of x over log of a, or natural log of x over natural log of a, or log base anything of x over log base the same anything of a. How can we use the properties of logarithms to solve equations, both logarithmic and exponential? Well, those 12 examples we ran through show you how to express our equations in either logarithmic or exponential form and solve for x. Why do we need to check for extraneous solutions when we solve logarithmic equations? Well, when we start with a logarithmic equation, we are implicitly restricting the domain of our possible solutions. When we go through the process of solving, we change from a logarithmic expression to some other form, exponential, and that new form has no restrictions on the domain, so it's potentially allowing us to find solutions that would not be allowed in our original expression.